Now it is more sensible. Check the format. Widgets. Properties. It is here. Settings. Okay.
Hello, sir.
Yeah, all right. I'm just starting. Sorry for that delay because I'm going to record this particular session. Just this is the model exam solution. I wanted to give this opportunity for those who cannot make to this particular class to just have an opportunity to see this. So it took a while. Thank you, guys. Rest in peace. Okay. I'm trying to record this. All right. Now I need to share the screen. Let's hope this whole thing works. All right. Is everything fine? I'm going to start solving these questions. That is the main task for me. And if there are any questions that you still have in the problem sheets, we still have Thursday an extra additional tutorial class still pending on Thursday. I can answer, but if there is time towards the end, I'll also use the time to answer any questions. All right. Can you please keep quiet if it is possible at all? I have uploaded all the marks in Canvas now. Please check your marks for test 1, test 2. I have also updated the test 1 marks based on your performance in test 2. All that is done and the marks are now available in Canvas. Please check, and if you find any discrepancies, please bring them to my notice. If you don't find anything, you don't need to do anything. Just rest in peace. All right. So let's solve these questions. Don't forget to write your name. And what is the no-slip condition? What causes it? The viscosity actually causes this. So I'm just writing, just like I'm writing an exam or condition leading to the stagnation of the fluid layers close to a solid surface due to viscosity is known as the no-slip conditions. This leads to the formation of a boundary layer where the velocity of the fluid flow will be varying from zero on the surface to the actual flow velocity at some distance from the free surface of the solid. How does the kinematic viscosity of liquids and gases vary with temperature? We discussed this in the class. In the case of liquids, kinematic viscosity, no. Kinematic viscosity is nu equal to mu over density. That is kinematic viscosity. And that nu increases, no, actually decreases. And in the case of gases, in the case of liquids, as the temperature increases, the resistance between the particles decreases, which is the root cause of viscosity in liquids. And so as the temperature increases, it becomes easier to make the fluid flow because the viscosity actually decreases. But in the case of gases, as you increase the temperature, the intermolecular collisions will increase, and they are the ones which are actually causing viscosity. And so that viscosity will be increasing with temperature. A small diameter tube is inserted into a liquid whose contact angle is 110 degrees. So contact angle phi is equal to 110 degrees in this problem. Will the level of liquid in the tube be higher or lower than the level of the rest of the liquid? So if you remember, there is the equation for viscosity. No, the capillary rise. Let's go to the formula sheet now. This is the formula sheet that we are using. The capillary rise, H, is 2 sigma S over rho G R cos phi. And that phi, when it is more than 90 degrees, cos phi becomes negative, and your height through which the liquid rises will be lower. And so all liquids with contact angle more than 90 degrees will have that liquid column below the free surface, such as mercury, and those with the phi, the contact angle less than 90 degree, they will be rising in a capillary tube because the cos phi is positive. So in this case, cos phi is negative, less than 1, hence It will be below the free surface level. What's happening here? Any question? So where is the where are the guys? Do you see? Oh yeah, they're here. Inline guys, admit. All right. Online guys, any other question? Is everything smooth there?
Yeah, we can see everything.
Very good. A submerged horizontal flat plate is suspended in water by a string attached at the centroid of its upper surface. Now the plate is rotated 45 degrees about an axis that passes through its centroid. Discuss the change in the hydrostatic force acting on the top surface of this plate as a result of this rotation. Assume the plate remains submerged at all times. If you go to the equations sheet, the fluid static pressure Fr is equal to P average times A. That P average is, if you forget that P0, rho GHC, and it is dependent on the density, the acceleration due to gravity, which are common for both cases given, and HC is the height of the centroid from the free surface, the depth of the centroid of the plane figure from the free surface. And in the problem that is given, what he's saying is, it is if that is the free surface of water, in one case, he is attaching a string there, and the plate is hanging on its centroid horizontally like this. And in the second case, the same plate is at some angle like this. No matter what, the height HC is the same. HC is equal in both cases. Therefore, the pressure or the hydrostatic force therefore Fr is equal to rho GHC times A. Everything is constant. Therefore, Fr, the net hydrostatic force acting on the plate, no matter what is the angle, remains the same. In both cases. All good? Can we move on? Consider a 3 kilogram copper cube and a 3 kilogram copper ball. What it means is copper sphere submerged in a liquid. Will the buoyant forces acting on these two forces be the same or different? Explain. So first see what is a buoyant force. Our equations for buoyancy are given here. Where is it? Fb rho Fg times the volume. That's it. Recalling the buoyant force Fb is equal to density of the fluid times G times, I'm using V dot for volume to differentiate it from velocity V. Okay, so that is the volume. What we have is a 3 kilogram copper cube and a 3 kilogram copper sphere. What do you think about the volumes of them? Are they equal or different? Cube and sphere, same mass. Because the density is the same. Density is mass per unit volume. And so in both cases, volume is equal to mass times density, or density equal to mass per unit volume. So therefore, the volume is equal to mass per density. Mass is the same, density is the same. So the volume should be the same, whether it is a sphere or whatever it is. Even if you make, what is it, the crown, as was worried about by Archimedes in his lifetime. It's a complex shape, but still it will have the same volume as the original volume of the gold or whatever metal that was taken in. So volume doesn't change. Only thing is surface area changes. The sphere will have the least surface area of all the shapes of a given mass. So that volume is the same. Volume is the same in both cases. Therefore, F beam is the same in both cases. Agree? Any question? What is stagnation pressure? Explain how it can be measured. So the sum of the static pressure and the kinetic pressure is known as stagnation pressure.
And I ended up getting soup. Soup was on clearance because he keeps getting returned because he's so wild. I love him so much. And how is it going to?
And we use a pitot tube for measuring the stagnation pressure, the static pressure plus the volume. So remember that. So if you put a pitot tube like this, so this is the stagnation point. The height through which the liquid column rises in that measures both static pressure there plus the V squared over 2G component. So from then on is the first two terms, sum of them is the stagnation pressure. Okay. All good. What is the hydraulic grade line? How does it differ from the energy grade line? Under what conditions do both lines coincide with the free surface of a liquid? So the sum of the static and elevation heads. Any problem?
I think they call it a pressure head instead of static.
Yes. Okay. Whatever you say, Jairam. So P over rho G plus Z. These two terms sum, and the Knowles equation is represented by the hydraulic grade line. All right. The energy grade line also includes the kinetic energy head. Which is V squared over 2g ton. When you consider static bodies such as lakes, the hydraulic grade line and energy grade line coincide with the free surface of the water body. Static fluid bodies such as lakes will have the hydraulic grade line and the energy grade line coinciding with the free surface of the water body. All right. What is the physical mechanism of heat conduction in a solid, a liquid, and a gas? So we have solid, liquids, and gases. In the case of a solid, heat is conducted by either vibration of the atoms or the movement of free electrons. Okay. Heat is conducted and also
Now that you know how to get in, don't forget to visit this hidden mark.
free electrons that are free to move around in a solid metal can carry heat or any solid substance. Also, the vibration of the atoms in the lattice structure will also cause transfer of energy. But in the case of liquids and gases, the randomly moving particles collide against each other, transferring energy. So collisions collisions between randomly moving particles will help transfer the energy from high energy state particles to low energy state particles. So this is the mechanism by which heat conduction takes place in the case of liquids and gases. Okay, some of you running some music, would you please check your microphones, please? In a certain experiment, cylindrical samples of diameter 4 centimeter and diameter 4 centimeter and height 7 centimeter were used. The two thermocouples in each sample were placed 3 centimeters apart. After initial transients, the electrical heater is observed to draw 0.6 amperes at 110 volts, and both differential thermometers read a temperature difference of 10 degrees Celsius. Calculate the thermal conductivity of the sample. So this is the thermal conductivity setup we have seen. So first, the power drawn from the electrical sources is VI. This equation is included in the formula sheet here. Electrical power Q dot equal to VI. So which is equal to 6 volts times 5 amperes, I think. No.
Hey, so can I throw it however I want?
No.
This challenge you can throw however you want. After all, I know the stat isn't your strong suit. You probably did mine really good.
5 amperes, correct.
About 30 meters, I guess.
Yes, I crushed it. Kind of more gorilla than tiger.
Um,
Well, in a sports
no, no. I'm looking at the wrong one, sorry. I'm looking at the next one.
Even though you love scary stuff, without me, you could never go to haunted places.
But we like being scared.
5 point
So, well,
6. Okay, I need to block somebody here.
besides, I want to be able to go home by 6. So if you two don't mind, I'll stay. I really like being in your club.
Hi, Ryan Jones, can you please mute your microphone?
Shop without using any cursed energy. If he's like Sonic. Well, it's already.
Is it good decision? That is a centrally placed heater, and that heat is going to be flowing in both directions, and each of the samples will be taking half of that heat. So therefore, Q dot is equal to W dot over 2, which is equal to 66 over 2, which is 33 watt in each sample. The area of cross section is pi d squared over 4, which is pi times 0.04 squared over 4, which is equal to 0.00126 meter square. And we know Q dot is Ka delta T over L. If you take high temperature to low temperature delta T, positive value. Therefore, 33 is equal to K times area 0.00126 times, there is a 10-degree difference. That's what he gave, divided by the thickness is given as 3 centimeters, which is 0.03. So from this, K can be calculated as 78.5714 watt per meter degree centigrade or Kelvin. All right. We solve problems like this in the exercise sheet. And where is this equation available? It is here. Q conducting is minus Ka dt over dx. But if you take that dt from higher temperature minus low temperature, you can use the positive relationship. If you use low temperature minus high temperature, there will be a negative value coming from the temperature difference, and that negative and this negative, they cancel. That's the only trick. All right, any question? An electric current of 5 ampere passes through a resistor, has a measured voltage of 6 volts across the resistor. So the electrical power drawn is VI equal to 6 times 5 equal to 30 watt. And the resistor is cylindrical with the diameter 2.5 centimeter and the length 15 centimeter. So this is the case of a thin wire going like that with a length 15 centimeter and diameter 2.5 centimeter. And the surface area over which it loses heat due to convection to the atmosphere is the circumferential area. So which is, so in case if you are in question, say if I blow this up like this is the diameter D and this is the length L. The circumferential length is 2 pi r or pi times D. That is the length of that circle times L gives you the overall surface area. That is the area of the cylindrical surface. So therefore, our AS here is equal to 2 times pi d squared over 4. I'm adding the two end surfaces also, pi d squared over 4. This is one area, and there is a pi d squared over 4 on the other side, a circle area on that end, and a circular area on this end, plus this lateral surface. So 2 times pi d squared over 4 is the area of this circle, plus that circle, plus pi dl is the area of the circumference of the cylinder. So which is equal to 2 times pi times 0.025 squared over 4 plus pi times 0.025 times the length is 0.15. So from this, the area of the surface is 0.0128 meters squared. The convective heat transfer from this is, where is the equation? Let's have a look into the equation so that you are familiar with these equations. So that is the heat transfer portion. Q dot due to convection is H times AS minus times TS, surface temperature, minus T infinity, the ambient temperature. That is the equation. Bring that here. H AS T surface minus T infinity. So that is equal to, therefore, 30 is equal to H times 0.0128 times the surface temperature is given as 90 degrees Celsius minus ambient temperature is given at 20 degrees Celsius. So we can use degrees Celsius in this equation, but only one equation, that is the radiation equation, which is here. Q dot due to radiation or Q emitted due to radiation is epsilon sigma AS Ts to the power 4 minus T surrounding to the power 4. You need to convert these temperatures into absolute units by adding degrees centigrade plus 273. Otherwise, the rest is normal. But in any equation, if you are getting both convection and radiation, better convection also convert to absolute temperature value. Otherwise, inconsistency will come into picture. So from this, we can calculate H as equal to 33.4821 watt per meter square degree Celsius. I'm not able to write very good in this arrangement because it's not very convenient with all the clutter around my screen in this small table. But I have done these solutions at home yesterday, no, on Sunday. I could write it better sitting at home. So I will upload that document when I am done with this. Not this cluttery, but I'm writing here because it gives you confidence when you solve these problems along with me. That's the main reason I'm writing this. Otherwise, I have solved this earlier. I could have just shown you the solutions, but I'm not doing that because practice is the best way to practice. All right, we finished 10 questions. Do you have any questions or do you want to ask me anything? Let me check what's happening here. Where are you? Where are they? Are they here? Yes, they're here. Online guys. Jaden Bakers, what is the question?
Hello. If we have a question with the thermal resistances, can you put that on the sheet?
What do you mean by that? Thermal resistances?
Is just so you don't have to like figure it out in the exam. You know, like when you take resistances in series.
Yeah, you have to just figure it out on your own because it's not
Okay.
a formula that I need to add anywhere because it's coming from the fundamental understanding. For example, so the resistance here is temperature Q dot equal to temperature divided by something. That something in this case will become L over Ka, length over Ka, that is the resistance there. And in this case, it will become 1 over HAS, or 1 over H times AS. And similarly for the other one. So I'm not giving any equations for that. Is it okay?
Yep, all good.
Yeah. All right. Derive the Bernoulli equation considering the forces acting on a fluid element moving along a streamline. What is the time? 4. So do you really want me to derive this again? Okay. What we are doing here is we are taking and there is a particle that is moving along a streamline like this. And we are considering a small particle of the fluid. So where on this side, the pressure is P, and on this side, the pressure is P plus an additional dP. And the weight of the fluid particle W acts downwards, and that is the normal direction. And we consider the component of this along this, and let's say this angle is theta. We know sigma Fs equal to mass times acceleration in that direction. But we have an expression A times ds is V times dV. This is one of our equations from kinematics. From this, we can write acceleration as V dV over ds. In a similar way, we can use V dV over ds for that part. And the net forces acting on this element are P times dA is the force acting here because we're taking that cross-sectional area as dA and the length of this element as ds. So P times dA minus P plus dP times dA, and the W sine theta acting in the negative direction, W sine theta, that is the net sum of the forces acting on the fluid particle along the displacement direction. This is equal to mass times acceleration, but that AS can be replaced by this term V times dV over ds. We can write mass is equal to rho times density times volume. But volume is rho times dA times ds. So that is the mass. And therefore, the weight W is equal to mass times acceleration due to gravity, which is rho dA ds times g. And sine theta here we are taking a small element ds along that direction, and that is your dz. This is dx, and that is the length of that element ds. And because this angle is theta, so we can write sine theta as equal to dz over ds. So by substituting these into that main expression, we can rewrite that equation as minus d p dA, cancelling out the other terms, minus rho times g times dA times ds times dz over ds equal to rho times dA times ds times v dV over ds. Now in this, we can cancel out dA on both sides of the expression. This ds and ds can be cancelled. This ds and ds can be cancelled. So this reduces to minus dP minus rho g dz minus rho times v dV equal to 0. But that v dV can be written as, say, v times dV is, that v can be written as the d over dV of v squared. Because if you differentiate half v squared, what you get? Half times 2 times v. 2 and 2 get cancelled, it becomes v. So this part is equal to v times dV. This is actually coming from the chain rule. And we can cancel these two. So v times dV is equivalent to d of v squared. So if you replace that, minus dP minus rho g dz minus rho times d of half v squared equal to 0. Dividing with the rho all through, we get minus. We can also kick out that negative sign all through. So dP over rho plus d of half v squared. I'm bringing that term earlier, plus g times dz equal to 0. Integrating this becomes integral dp over rho. For constant rho, it becomes p over rho plus integral d of anything is integral dx is x. Like that, integral d of half p squared is half p squared plus gz equal to 0. This is Bernoulli equation along a streamline. What? Move on. Any question? Jayden, are you there? So this problem is very similar to the friction problems we solved in statics, but one half is dry friction, the other half is when there is a liquid fill between them, how does the force change? So for that, and if you recall your statics course, we need to draw the free body diagram of this. And the free body diagram is the weight W acts vertically downwards, and we resolve this into an X component and Y component. We call this as WX, this is WY, and if this angle is 20 degree, we already saw many times, this angle is 20 degree too. And your external force F is acting horizontally there. So if we want to resolve this into a component perpendicular to the plane and a component parallel to the plane, this is your F, this is Fy, Fx, and that angle is again 20 degrees. There will be a normal reaction coming here, N, and a frictional force. This could be the friction force. We call that as F. Let's call this as F friction. If it is frictional force, in part A, this is frictional force, or it could become the F shear force or Fs. When there is fluid film between the two, it becomes the shear force. Okay, case A. In the case of dry friction, sigma Fy equal to 0 will give you N minus Fy minus Wy equal to 0. He is asking you to calculate what is that force F that you need to apply horizontally to move it with a constant velocity. Remember, constant velocity case is equal to static equilibrium case. Therefore, from this, N is equal to Fy plus Wy equal to F sine 20 plus Wx is, W is given as 150 Newton straight away. So 150 sine 20, which is equal to 51.3030 Newton, and Wy is equal to 150 cos 20, which is equal to 140.9539 Newton. Wx and W1 are known. So N is plus Wy, which is 140.9539. That is the normal reaction. But the friction force Ff will be the maximum frictional resistance possible because it's already in motion. And the only coefficient of friction we are given with is 0.27. We consider that as the kinetic coefficient of friction, 0.27 times F sine 20 plus 140 times 9539. So from this, the friction force is equal to 0.0923 F plus 38.0576 after simplifying that equation. We still don't know what that force F applied is. We are waiting for that. So now we consider sigma Fx equal to 0, which gives Fx minus Wx equal to minus friction force minus F equal to 0. Why am I applying static equilibrium condition there? Because it is said that it is moving with constant velocity. Constant velocity case is equivalent to static equilibrium case. We did this in earlier problems also. You should be able to recognize this. Okay. So from this, F cos 20 minus 51.3030 minus 0.0923 F minus 38.0576. I'm substituting what is F equal to 0. In this, F is the only unknown quantity. If you solve, we get friction force. The force to be applied is equal to 105.4536 Newton. So that is the force that is required to push this block upwards with a constant velocity. This is from statics. There is nothing new here. Now comes the new part, that is with fluid film. So when we put a fluid film, friction will be gone. There is no friction anymore. So instead of friction force, there will be a new force coming in. That is the shear force applied by the fluid film. And that shear force is, we know, F shear force is equal to tau, the shear stress applied by the moving body on the film times the area of that shear. But tau in Newtonian fluids is mu times du over dy, where du over dy is the slope of the velocity profile times as. And where are these equations? Let's look at fluid statics here. If you come here, can you see this is actually, no, wait, capillary rise. Can you see tau equal to mu du over dy? That is the shear stress in the case of a fluid film. But what we are writing is the force. Force is shear stress times area on which the shear is acting. That's the equation we are using here. So force is stress times area, because stress is force per unit area. So the shear force is stress times area, but that stress is mu du over dy from this equation. Now what is mu? Therefore, Fs is that mu is given as in this problem. Can you check? 0 point viscosity, dynamic viscosity mu is 0.012 Pascal second. So that is what we need to use, 0.012 times the velocity is changing when you apply a film, when you create a, say, an oil film here between that surface and this one. And I am showing that in an exaggerated manner like this. Say that is the oil film. And this is your solid that is moving with a velocity 1.10 meter per second. The oil film on this surface will have zero velocity, and here its velocity will be 1.10. In a height, he gave you the film height is 0.40 millimeter thick. So this is 0.40 millimeter, and the velocity is changing from 0 to 1.10 meter per second. So du, the variation in the velocity is 1.10 divided by the thickness of the film dy is 0.40 millimeter, and that you need to convert to meters. So 0.4 in meters is 0.0004 times the area is what are the dimensions of this? This is 50 centimeter. The 30 centimeters is the thickness. The width is 20 centimeter. So the area on which it is resting on the fluid film is 50 times 30, not 20. No, 50 times 20. So 50 centimeters is 0.50 meters times 0.20 meters. And from this, we get the shear force acting between the bottom surface of the crate that is moving and the fluid film as 3.3 Newton. This is the resistance to the movement, not the actual friction force. Now, using again, we don't need to go through all of that, whatever we did earlier. Now, what we have is along the x direction, the horizontal component of Fx minus Wx minus F, that shear force must be equal to 0. So which is F cos 20 minus Wx is 51.3030 minus Fs is 3.3 equal to 0. From this, the force that is necessary to move this is 58.1073 Newton. Agreed? So if you are just moving that block in dry condition, you need a force of 105 Newton approximately. And if you are having the oil film, the force necessary became almost half. Now you see how the oil that we use between moving surfaces actually helps in reducing frictional effects. Any question for me? Remember, this is not the true time to solve. I'm explaining, I'm bringing the background, I'm covering the foreground, and then also solving. So don't consider this as the true time to solve. You need to be just solving them without worrying about too many things. Okay, what's happening here? Online. Is everybody safe and sound? Emerson?
Safe and sound, sir. Thank you.
Wow, okay. Any niceties to exchange with anybody here, friends, relatives, and anybody else?
I don't know, but I'll say hi to everyone. Hi, everyone.
Guys, this is the last chance for you to say bye to anyone because this is our last session, maybe for your lifetime, isn't it? Pardon? This is what people are, okay. This is what people are seeing.
Hi.
Okay, anybody wants to turn on their video cameras? This is the last chance, please. Online guys.
Hello.
So who is the friend here? All right. All right, that's great. Okay, I think that's enough. Thank you. Let's continue. Very interesting problem. Very interesting problem. This actually joins the fluid statics with the normal statics that we did earlier. Let's see what happens. A 6-meter high, 5-meter wide rectangular plate, which is this one, blocks the end of a 5-meter deep freshwater channel. That is what it is. As shown in this figure, the plate is hinged about a horizontal axis that is here at A, along its upper edge through a point A, and is restrained from opening by a fixed ridge at point B, that is this one. Determine the force exerted on the plate by the ridge. Because this fluid is pressing against this plate, and the plate is restrained from movement at the hinge and also at this point. So this fluid pressure will be acting on this one, and the point B and point A will offer resistance. He's asking what is the resisting force at ridge B. So we need to consider the free body diagram of the plate in this case. So free body diagram. Let me enlarge it a little bit. And that is A. And at B, at A is a hinge. When you remove a hinge, what kind of reaction forces we put? Need to add a horizontal unknown force AX and a vertical unknown force AY. We don't know both of them. And at B, it is pressing against a vertical stopper. Neglecting any horizontal resistance, we can simplify that as a force acting in the x direction like this. That is the force he's asking you to calculate. And what will be the net effect of this hydrostatic force acting due to the liquid column? We can simplify that as one single force Fr, and that Fr will act at some distance like this. And now under the action of all these forces, that plate is in static equilibrium. And so we can now apply static equilibrium condition. But the only thing that is unknown is where is Fr? And at what distance is it going to act? And by the way, we need to mark the water level here. So the water is up to that level. And our dimensions are, this is 1 meter. And that is 5 meters. And our Fr force acts at a vertical depth equal to Yp or Hp from the free surface. We need to calculate both Hp and Fr, then we can solve this problem. And where are these available? These available. If you go to the formula sheet, the hydrostatic force acting on a body is Fr is equal to P0 plus rho g yc sine theta A. P0 is the atmospheric pressure, as we discussed in the lesson. It acts on both sides of the plate. We can neglect that. So if you remove that, this is rho g hc times A. That is the friction, the hydrostatic force. Let us calculate that first. Fr is equal to rho times g times hc times the area. All right. The density of water is 1000, 9.81 times the center location is from the free surface, it is at a depth of 2.5 meters, isn't it? Half of that height. So which is 5/2. That is the height of the centroid from the free surface. Vertical plate times the area of the plate is 5 meters by 5 meters. So this will give you FR as equal to 613,125 Newton. So that is FR. Then at what depth it is going to come? YP. For that, the equation is YP is YC plus IXXC over YC plus P0, blah, blah, blah. The P0 term we can neglect because we are neglecting atmospheric pressure on both sides. So this reduces to YP equal to YC plus IXXC over YC times A. That is the simplified form. I told you in the class, I will not be simplifying these equations for every condition. So YP actually equal to YC plus IXXC divided by YC times area. It's coming from that equation. Let's substitute what we know is equal to 5/2 plus IXXC is the moment of inertia of a rectangular plate about an axis passing through the center and parallel to the base is BD cubed over 12. So this is 5 times 5 cubed over 12. Remember and recall the statics course. And if that equation is needed, I will give you that equation. You don't need to remember that. Times YC is again 5/2 times the area of the plate is again 5 times 5 meters square. So from this, we get YP is, it is also HP because this is 90 degree, sine 90 is 1. So HP is YP sine theta. The theta is 90 degrees. So HP and YP both are same, is equal to 3.3333 meters. So that means this distance is HP is equal to 3.3333 meters. From the free surface of the liquid, it is acting at a depth of 3.3333 meters. Now, if you want to calculate what is Bx in this free body diagram, we take sum of the moments about point A equal to 0, so that Ax and Ey are avoided. So, writing sigma A MA, moments about point A, sigma MA equal to 0 will give you FR times HP minus Bx times 6 equal to 0. Therefore, FR is 613,125 times the distance is 3.3333 plus extra 1 is there minus Bx times 6 equal to 0. From this, we get Bx is equal to 442.8091 kilonewton. That is the reaction at the bottom. Now tell me if there is any question on this. Anybody? All right. Anybody? Online? Anyone having any question? Emerson.
No question. question, sir. Thank you.
Very good. Ryan Jansi.
No question. No question, sir.
Wow, what is this, man? Okay, good. Let's move on.
Help me.
Water is flowing through a venturi meter. So a tube like this with decreasing diameter and increasing diameter is a very popular device in fluid mechanics. If you go into any hydraulics laboratory, you will find this. It is quite an interesting device. People who are taking up, mechatronics or mechanical engineering or marine engineering, they will be actually going through a lot of the use of these things later on. But anyway, this is what is known as a venturi meter. So it is having a varying cross section like this. So the diameters are 7 centimeter here and 4 centimeter here. The pressure is measured to be 308 kilopascals here and 200 kilopascals here. Neglecting frictional effects, determine what is the flow rate of water. By the way, no matter how the cross section varies, the net flow rate through this venturi meter, the net flow rate remains the same everywhere. But the velocity will change according to the cross section. So first things first, there is something called the continuity equation. According to that, where is it in our formula sheet? Continuity equation, AI VI equal to constant. Area times velocity is constant at any section. What it means is A1 V1 equal to A2 V2 equal to A3 V3 and so on. So first, if I use that equation, our D1 is 7 centimeter, which is 0.07 meter. D2 is 4 centimeter, which is equal to 0.04 meters. We have A1 times velocity 1 equal to A2 times velocity 2 according to continuity equation. So from this, V2 is equal to A1 over A2 times V1, which is equal to area 1 is pi D1 squared, area 2 is pi D2 squared. This can be written as D1 squared over D2 squared times V1. So therefore, V2 is equal to 0.07 squared over 0.04 squared times V1, which is V2 is equal to 3.0625 V1. We got one relationship between the velocity at V1 and velocity at V2. We don't know both of them now, but we can apply Bernoulli's equation between points 1 and 2, and that is P1 over rho g plus P1 squared over 2g plus Z1 equal to P2 over rho g plus V2 squared over 2g plus Z2. And because these are all central points, if I take that central line as the datum, we have Z1 equal to Z2. So we can cancel Z1 and Z2. And the remaining equation is P1 over rho g plus V1 squared over 2g equal to P2 over rho G plus V2 squared over 2G. We can also cancel the G from this equation. Let me remove G's because they are there throughout in the denominator. So this is the expression we are getting. So therefore, V1 squared over 2 minus V2 squared over 2, but that V2, I will replace this as 3.0625 V1 squared over 2 is equal to P2 minus P1 over rho. So from this, therefore, V1 squared minus 9.3783 V1 squared is equal to 2 times 200 minus 380 times 10 cube over 1000. So there is a negative sign coming on the left side and the negative side coming on the right side. They can be cancelled, and finally we can simplify this as 8.3783 V1 squared is equal to 360. From that, V1 is equal to 6.555 meter per second. Once you know the velocity V1, the flow rate, that's what he's asking. Therefore, flow rate, the rate at which liquid is flowing is area times velocity, because that gives volume, but volume meter per second is velocity. So volume per second, that is the flow rate. You can use, you need to use A1 times V1 velocity. So flow rate V dot equal to, which is equal to pi over 4 times A1 is D1 is 0.07 squared times 6.555 meter per second. So from this, the flow rate V is equal to 0.02523 meter cube per second. That is the flow rate. What do you think? Applying Bernoulli equation, we are getting one equation, but there are two velocities unknown. The second relationship is coming from the continuity equation, and that's it. Solve both of them together, you get that unknown velocity. Yep. Yeah, squared the number, and that 2 I cross multiplied and took it to the right side. So 3.0625 squared is 9.3783 times V1 squared.
Hello, sir.
That squared is this. But 2 I took to the right side and took 2 is common to both of them, so I took it to the right side. I took 2 common here and took it to the right side, so it becomes 2 times P2 minus P1 over 1000. So Jayden, do you have any problem? Yeah.
You know the question we had with the hose, and we assumed that the V1 is 0.
Yeah.
Is there any like difference in area that like, you know what I mean, right? Like if one area is much larger than the other, you can say that, or you just look if they give you it in the question or not.
You need to look at the question, and depending on the data that is given, we need to use an appropriate scheme of, thinking
Okay.
inside. Yeah, it's not
No
universal for everything. This is a very carefully calculated. A Venturi meter is a scientific device. We have complete control on the areas and how the areas are changing. And also the velocity is not abrupt. Can you see that smooth curve there ensures Newtonian fluid flow and also streamlines going as streamlines. And that is the beauty of a venturimeter. So the Bernoulli equation perfectly applies to this case. But if a boy is trying to block the hose with a finger, that is not, a controlled experiment. So we can't take it for granted there. Okay, anyway, move on because you can also calculate by using A2 times V2. So you need to calculate, you substitute what is V1 in this equation and calculate V2, and A2 times V2 also will give you the same flow rate. It doesn't change. If you check that, if it varies, then I will not teach fluid mechanics anymore. Okay? It should, because it's coming from the continuity equation. The flow rate should be the same whether you use A1 times V1 or A2 times V2. Because it's the same, I did not waste any time and I just used A1 times V1. All right. Okay. Now, again, we are running out of time. I need to move it fast. Can you please keep quiet, sir? If you can. Air at 20 degrees Celsius with a convection heat transfer coefficient of 25 watt per meter squared Kelvin. So there is a convective heat loss coefficient here, 25 watt per meter square Kelvin. Blows over a horizontal steel hot plate. Thermal conductivity K equal to 43 watt per meter Kelvin. The surface area of the plate is 0.38 meters square with a thickness 2 centimeters. The plate surface is maintained at a constant temperature of Ts equal to 250 degrees Celsius, and the plate loses 300 watt from its surface by radiation. Calculate the inside surface temperature of the plate. So this is the case of combined heat transfer. Let's have a look at that. Keep quiet, keep quiet. So there is a plate and there is air flowing on the surface of the plate. And the thickness of the, all right, I need to take some action here. Sorry for that. Okay. All right. So what he says is this steel plate is losing heat. It is flowing from here and is going all the way there.
This is all recorded, by the way.
And the thickness of this plate is 2 centimeters and the top surface is at 250 degrees Celsius, and the surface on the inside, this is the temperature that we don't know. Let's call that as Ti is watt. And there is ambient air at 20 degrees Celsius. He gave the plate is losing heat. The plate surface is measured and the plate loses 300 watts from its surface by radiation. So Q dot due to radiation is 300 watt, which is already given. So let's solve this problem. We know Q dot due to convection. Where is this equation? It is Q dot due to convection is HAS Ts minus T infinity is equal to the H value is HAS times Ts minus T infinity, which is equal to your heat transfer coefficient due to convective heat loss is given as 25 times the area of cross section is given as 0.38 times the temperature of the surface is 250, ambient temperature is 20. I told you, you can use degrees Celsius for this equation. And from this, we get 2185 watt. That means 2185 joules of energy is lost due to convective heat loss per second from that surface. Then what is the Q dot radiation is straight away given. That means this surface is losing heat due to radiation and also convection. So it is a combined heat loss there. But the total heat that is gained and is transferred through conduction, Q dot conduction. So that is the heat that is flowing inside and flowing through the plate due to unidirectional conduction. Under steady state conditions, whatever heat is flowing through the plate due to conduction should be the same as the heat that is lost due to convection and due to radiation. So this must be equal to Q dot due to convection plus Q due to radiation. But we know the heat loss due to conduction, you come back to this equation, is Ka dt over dx. You can kick out that negative sign if you're using high temperature minus low temperature. Let's do that. Therefore, K times A surface times the inside temperature minus the outside surface temperature divided by length L must be equal to Q due to convection plus Q lost due to radiation. So from this, we can write 43 is the thermal conductivity, 0.38 thickness times the inner surface we don't know, outer surface is at 250 divided by the thickness is 0.02. So that 0.38 is the area of the plate. This must be equal to 2185 plus 300. So from this, Ti is equal to 253.0416 degree Celsius. That is the answer. Any question? Online, anybody having any question?
No questions.
Very good.
Okay.
Can I move on? I will immediately upload these solved versions of this these sheets online, but the video, remember, I'm recording. It takes a lot of time for me to upload the video. It's not that easy. So I need to extract it from here to the, share directory, and from there Panopto. It takes a lot of time. So I cannot assure you that it would be online today. It may be only tomorrow. All right. Seventh question. The diameter of one arm of a U-tube is 5 millimeter, while the other arm is large as shown in this figure. If the U-tube contains some water and both surfaces are exposed to atmospheric pressure, determine the difference between the water levels in the two arms. The contact angle of water is phi equal to 0. The surface tension and density of water at 20 degrees Celsius are sigma S is 0.073 Newton per meter and rho is 1000 kilogram per meter cube. This is the case of capillary rise. And for capillary rise, we have an equation here, which is H equal to 2 times sigma S over rho GR times cos phi. let's take that equation into this. We know H is equal to 2 times sigma F
Shush.
cos phi over rho g r. So from this, we can substitute 2 times sigma s is the surface tension 0.73 times cos 0 divided by density 1000 times G 9.81 times the diameter is 5 millimeter, and so the radius is 2.5 millimeter. In meters, it is 0.0025 meters. So from that, H is equal to 0.005953 meters. That's it. That is the height difference. So in simple terms, this is H is equal to 5.953 millimeters. All right. Let's solve the last one. To defog the rear window of an automobile, a very thin transparent heating element is attached to the inner surface of the window as shown in this figure. So this is the heating element there. All right. A uniform heat flux of 1300 watt per meter square is provided to the heating element. So the heating element is getting Q dot heat flux into it. For defogging, the thickness 0.5 millimeter. So the thickness of the window is 5 millimeter. The glass part is 5 millimeter. The interior temperature of the automobile is 22 degrees Celsius. That is the inside. And the convection heat transfer coefficient here is 15 watt per meter square Kelvin. So that is the heat loss, because that film on the inside is heating up. Some part of that heat will be lost to the interior of the car, and some will be conducted into the glass plate, and some of that the one that is conducted into the glass plate will also be convected to the outside, because you are solving the problem for steady state. That means whatever is going in should leave at the end of that. So the problem is like this. We have say this is your heating coil. That is the thin film of the heating coil. You are sticking to the surface of the glass at the back, the rear glass. And then you have the glass like this. Let's say that is the glass. So the thickness of this is very small. So that is 0.005 meter. And we are losing heat from the surface due to convection here. And the temperature there is -5 degrees Celsius. And the temperature inside the car is 22 degrees Celsius. Now, we are supplying heat into this, and that heat, instead of Q capital, he gave that as per unit area, so which is Q dot. I told you all these equations you can also use as per unit area. In that case, it is called heat flux. We are using small Q dot for that. So that is the heat that is flowing into this element. Some of this heat will be lost due to convection here. And we have the convective heat transfer coefficient here, HI, as equal to 15 watt per meter square Kelvin. And there will be a conductive heat transfer. So let's say due to the heating, that surface is at T1 And also that surface is at T1 because the whole of that film is heated to a constant temperature T1. And heat will be conducted due to conduction in the glass, which is equal to 1.2 watt per meter Kelvin. And let's say the temperature on the outside edge of the glass panel of the window, that temperature is T2. And the outside temperature is -5. Let's call this as T out and call this as T in. Inside the car is 22 degrees, outside is -5 degrees. Heat is flowing both ways in this problem. It is not going from inside of the car straight to the outside or from the outside to the one side, not in one direction. In problems like this, don't use the resistance method. Just use your normal calculation. That is, what is the total heat transfer per unit area? For example, Q dot due to convection on the inside, that is this one, Q dot due to convection on the inside is that heat it is losing this side. What is the equation for Q dot convection? H AS TS minus T infinity. When you use Q small q dot per unit area, we just kick out that area and write the expression. So is equal to H times HI times the temperature on the surface T1 minus the temperature in the ambient, which is inside the car, Ti. So which is equal to 15 watt times T1 minus 22, where T1 is the temperature of the heating element. Now Q conducted in the glass part is, this is conduction. The equation for Q due to conduction is Q due to conduction is Ka dt over dx. Can you see that? But that A should be removed when we are using heat flux per unit area. That's the only difference. So Q small is equal to K times the high temperature is T1 and the low temperature is T2 because it is changing from T1 to T2 here. So T1 minus T2 over the length L. This is equal to 1.2 times T1 minus T2 divided by 0.005 is the thickness. So that is the conduction part. And there is another component, the convective heat loss there, Q due to convection outside, lost from the outer edge of the glass. So Q dot due to convection on the outside is equal to H on the outside times T2 is the temperature on the surface minus T outside. So this is equal to 100 times 100 is the heat transfer coefficient that is given due to convection on the outside edge times T2 minus of -5. Remember, it is not -5, minus of -5. So that gives you this as equal to 100 times T2 plus 5. But whatever heat is being conducted through this is our Q dot due to conduction in the glass part. That one and the heat loss due to convection here, they must be equal because some part of this heat is going into the glass conduction and then it is being lost due to convection. So our question here is, we know, but Q dot due to conduction in the glass must be equal to Q dot due to convection on the outside because it's the same heat that is flowing across. So from this, Therefore, we can equate 1.2 times T1 minus T2 over 0.005 must be equal to 100 times T2 plus 5. And therefore, 1.2, let me write this a little to the left side, if you don't mind it. I have 2 minutes time. I cannot finish in 2 minutes. Just wait for a couple of minutes more. And therefore, 1.2 times T1 minus T2 and divided by 0.005 is Q dot due to conduction is equal to 100 times T2 plus 5. Simplifying this, therefore 1.2 times T1 minus T2 is equal to 0.50 times T2 plus 5. So T1 minus T2 is equal to 0.4167 T2 plus 2.0833. So from this, T2 is equal to 0.7059 T1 minus 1.4705. We are getting a relationship between T2 and T1. So we can't go much further than that with that. We need to go to the other equation, that is it's too big. We know Q dot, the heat that is generated here, Q dot is shared by this convective heat loss plus this conductive heat taken away. Some of it is going to the left into the car and the rest is going into the glass due to conduction. Therefore, we know the total heat flux into the heating element must be equal to the Q dot due to convection on the inside going into the car plus Q dot due to conduction going into the glass. Agree? So from this, we know 1300 is the heat going per unit area. It is given 1300 watt per meter square. That is equal to, we know this is 15 times T1 minus 22. And this is plus 1.2 times T1 minus T2 divided by 0.005. Can you see T1 and T2? This is an expression, but T2 is this quantity. If you substitute it into this T2, this will reduce to one single equation with the T1 unknown. We can calculate the T1, and that is what is asked. So therefore, 1300 is equal to 15 times T1 minus 22 plus 1.2 times T1 minus, instead of T2, I'm writing this one, minus 0.7059 T1 minus plus 1.4705 divided by 0.005. I just substituted what is T2 in that. Simplifying this, I get therefore 15 T1 minus plus 240 T1. I'm taking all the T1s to the left side, minus 169.416 T1 minus 330 plus 352.92 is equal to 1300, or 85.584 T1 is equal to 1277.08. From this, T1 is equal to 14.9219 degrees Celsius. That's it. I'm only 3 minutes beyond 5 p.m. So we are still comfortably completing this solution. Is that clear? What is it? The Q? Yeah, that the T1 is where? T1. Okay, I'll check that. I'll check that last one. Okay. Let you know on Thursday then. But that is how you solve these problems. Any other question?
No. No.
All right. So we stop it there then. And all the best. And I will see you on Thursday in the class, which is the last class.
What a drag.
We will wind it down on Thursday, and Friday evening. The test will be in similar lines to what we have seen just now. All the best.
Thank you very much, sir.
All right, bye, sir.